This is Lab 3 with Group 7. Group 7 consists of Erin Lee, Jessica Smith, and Kelly Snedeker. In this lab, we were given the truth table for the lights on a car. From this truth table, we can derive the Boolean equation and reduce that Boolean equation for each of those lights using K-maps. We need 4 different K-maps for each of the different lights. Shown here are 2 examples of those K-maps. One is for the left front light and one is for the right back light. Next, we will use the left back light as our example. In this slide, you can see to the right is the K-map for the left back light. Shown in green, red, and yellow are the different loops for the left back light equation. From these, we can get the min-term expression for that light, and then we can derive the Boolean equation from that. In part 3, we will get the full Boolean equation from the truth table, which is highlighted in red for the left back light. All of the ones are highlighted in blue. As you can see, this is the full non-reduced Boolean equation here to the right. Now we will use the K-map to simplify that Boolean equation. To the left here is the K-map for the left back light. Highlighted in red is one of the loops, which corresponds to C and L. Highlighted in green is R and S, and highlighted in blue is S and L naught. We derive these simplifications using the K-map. Here is the full simplified equation for the left back light, which is C and L, or R and S, or S and L naught. Here you can see all of the simplified equations for each of the 4 different lights. Here we use Logisim to create a circuit that uses AND, OR, and NOT gates to show and to output the correct outputs using these simplified equations. Here we've used 2 NOT gates, 6 AND gates, and 2 3-input OR gates. Now this is one way that it could be done, but this way can be expensive to make. So we will use this and convert it into a ROM circuit. In order to convert that into a ROM circuit, we must use the truth table again. And in this truth table, we are going to convert the 4 outputs into hexadecimal numbers. The 4 outputs can be used as a 4-bit binary number, which we can then convert into a hexadecimal number, and then input that into the ROM circuit. Shown here are the conversions from the 4-bit binary code to the hexadecimal number. On the lower right corner is shown a ROM circuit in which we have programmed each of the hexadecimal numbers into the correct location. Shown here is the full ROM circuit with the 4 inputs and the 4 outputs. It is important to note that the least significant bit and the most significant bit should correspond to the least significant bit and the most significant bit on the splitter. For example, the clock input is the least significant bit in the truth table, and it is wired to the 0 or the least significant bit on the splitter. Now, we can see here that this ROM circuit is exactly the same as the one in the previous slide. Now, if we were to change the inputs to 0, 0, 1, 1, we would see that the highlighted section would go to the 3, which in turn would change the output to 0, 0, 1, 1. This shows that the ROM circuit is working correctly, as it is corresponding to the correct outputs with the inputs, as shown in the truth table. In this lab, we have concluded that using a ROM, or a lookup table as it is also known, can be easier and more cost-effective than using a large number of logic gates. Some of the applications for using a ROM circuit, as we saw in this lab, were for the turn signals and brake lights of a car. And we also decided it could be fun for a Christmas light display. Thank you for watching.